Micronaut is a modern JVM-based full-stack framework for building microservices and serverless applications. It's designed to be lightweight, fast, and easy to use, with a focus on simplicity and productivity. Micronaut was created by the team at Object Computing Incorporated and is open source under the Apache 2.0 license. It was designed to be an alternative to other Java frameworks such as Spring and Play, with the goal of being more efficient and easier to use. There are a number of benefits to using Micronaut for web development. It uses ahead of time compilation to generate efficient native code for a variety of platforms, which means that Micronaut applications can start faster and use less memory than traditional applications. It has built-in support for dependency injection and inversion of control, which makes it easy to create modular, reusable code. It has built-in support for HTTP clients, servers, WebSockets, and other features. This makes it easy to build web applications that can communicate with other services and APIs. In this course, we'll be learning how to use Micronaut to build web applications that are scalable, maintainable, and easy to deploy. We will cover topics such as defining routes and controllers, working with relational and non-relational database systems, implementing Kafka integration, implementing Redis integration, and testing. MySQL is an open source relational database management system. It is free and widely used. MongoDB is a document database. It stores data in JSON-like formats called BSON. Redis is an open source in-memory data store commonly used as a database, cache, streaming engine, and message broker. We will cover the cache use case, and you're encouraged to explore other use cases. Kafka is an open source distributed event streaming platform used by many companies for high-performance data pipelines. Throughout the course, we will combine some of the tools mentioned previously to create, read, and manipulate data. By the end of the course, you will have a good understanding of the Micronaut framework, and you will be able to start working with other Micronaut integrations to build your own projects with confidence. Okay, let's get started. To set up a new project, open up your terminal. We're using Java 11 for this course. Okay, I have JDK 11 here. That's good. To create a new app, use the mn create app command, followed by the name of the application. The name of the application is product catalog in this case. That's what I choose. You're free to choose what you like. It's a good idea to include a package name when you create the app. So I'm going to include a package name here. My package name will be com.learnerqt. Feel free to use whatever package name you like. Next, I want to use Kotlin, so I'm going to specify it here. You will still be able to follow along if you use another programming language. I will go ahead and select Gradle Kotlin for my build system flavor. That's it. As simple as that, the application is created. Let's take a look and see the structure. I'll open up the application folder in my IDE. I use IntelliJ, but you can use any IDE that you are comfortable with. Let's check out the build.gradle file. This is just a default setup. It has the basic things for this application to run. And if you notice here, we have a source main Kotlin. In here, you will see the main application source file. In the test folder, there is a product catalog test. Newly created applications usually have at least one test file. This test simply ensures that your application can run. And I like it because sometimes I use it to know if my application is set up correctly. Let's run the application test to see if it works. Subsequent runs will be much quicker. The test passed, so we know that the application can run. Let's run the application. Notice that the startup time is really small and the server is running on port 8080. If you can click on the link or you open up your browser. Let's open up the browser. I can see the page. The message on the landing page tells me that something is responding to the HTTP request. Let's stop the application, and that's it. That's how to set up a new project. In the next lesson, we'll create a simple Hello World application. See you there. Welcome back. In this lesson, we will learn how to create a simple Micronaut controller. The controller will have an endpoint that returns Hello World when called. The first thing we will do is to create a package for the controller. Let's call it the controllers package. Inside the package, we will create a class. That class will be responsible for the routing of traffic. Our class name will be Hello Controller. All controllers in Micronaut have to be annotated with the @controller annotation. This is what Micronaut uses to provide the features that all controllers need. The @controller annotation can take parameters, and you can explore those parameters if you hold down the control key and click, or hold down the command button and click if you're using a Mac. For this controller annotation, we're going to add a route. This means that when an HTTP request with a matching URI is received, the controller will handle the traffic with the matching function. Our function or method name is sayHello, and we will annotate this function with a get annotation. That get annotation means that when a get request is received with a matching URI on this controller, this is the function that will handle that request. We have something really simple here. We are going to return Hello World, just a string, when a get request is received. Let's try it out and see how it works. I'm going to start the application. Okay, application has just started. Let's check it out. Let's go to our browser. Localhost 8080/hello. We have Hello World. Very simple. In the next lesson, we will create a simple test for this endpoint. See you there. Welcome back. In the previous lesson, we created a Hello World controller with a simple endpoint that returns Hello World. In this lesson, we're going to write a simple test for our Hello World endpoint. Let's create a package called controllers inside the test folder. It should match the package of the controller we want to test. Then we'll create a Hello Controller test file. Annotate the test file with @Micronaut test. The annotation is needed so that the class will be treated as a test class by Micronaut and be given some features needed for Micronaut tests. Let's create a test function where we can specify the behavior we want to test. We will set up conditions that we want to test, perform a few actions, and then verify that the outcomes match our expectations. For this test, we're going to use an HTTP client to make requests to the application endpoint. We will then compare the endpoint response with what we expect. If the response matches our expectations, it means that the assertion condition was met and that the test passed. However, if the expected value doesn't match the return value, then the test will fail. I'm going to inject a HTTP client object so Micronaut can provide an instance when the application starts. Next, we'll need to create a HTTP GET request. Type is a string. Remember to import the correct package and give it a URI of /hello. The client will make a request via the retrieve function. The response will now be checked with an expected value. Import the necessary assertion functions from JUnit. If the test fails, we'll figure out why and fix it. If it passes, then that's good. We'll use the client to make a request to that endpoint and then check the response from the endpoint with an expected value. We're going to assert that the string returned is equal to hello world. And then we'll check that the response is not null, that is not empty. Import the right assertion functions into your code. And don't forget to annotate your test function with @test annotation. Let's run the test. Okay, so this test failed. It says HTTP client has not been initialized. And the reason for that is that we did not annotate the HTTP client with @inject. Anytime you want something to be injected for you, you have to annotate it with @inject. Now, we have a different kind of error, which is good, and it looks like we made progress. It failed because we did not assign a host to the client. Let's assign that and run the test again. Great. The test passed and our application is behaving as expected. Welcome back. In the previous lesson, we wrote a controller test for a very simple hello world endpoint. In this lesson, we're going to touch on Micronaut configuration injection. We're going to discuss different ways through which you can retrieve values stored in your Micronaut configuration file for use within your code. The default Micronaut configuration file is the application.yml file. Let's open it and add a few items to it. I'll add a name to the config file and then we can explore different ways to pull in this value into the code. Let's create a new class called myUtilityClass and annotate it with @singleton. Let's add a logger to this class. Next, we'll use the value annotation to bind the config value to a variable in this class. In this case, what we're trying to bind is the name variable that is in our application.yml file. We will bind it to this name variable that is the string. Notice the string inside the value annotation. It matches the config block inside the application.yml file. Let's write a function that will return hello name as a string. The name is going to be pulled from the configuration file. Let's create a new test file inside the config package. Let's call it my utility class test and annotate it with @Micronaut test. Let's create our first test function. Let's call it say hello with annotation returns correct greeting. We are going to inject my utility class. And then our expected return value is hello Jane, as we can see in the config file. And then we're going to call my utility class and call the function, and then assert that the expected value is equal to the greeting. Let's run the test. And the test passed. Next, we're going to try to override the configuration value. You can do this by annotating the test with @properties annotation. Let's see how to do that. So you add the property annotation, and then you give it a name. The name should match the value, the config block that you're trying to override, and then the value should be equal to whatever it is, whatever value you want to use to replace that config value. In this case, we want to replace Jane with John. And then we're simply going to do the same thing, define an expected greeting. We define an expected greeting, which is hello John, and then call the utility class method and assert that the utility class method returns hello John. Let's run the test. The test passed. Awesome. The next thing we'll do is to use immutable config classes. We're going to create a class inside the config package. Let's call it myconfig. It's going to be a data class. We'll add the name of the value that we want to pull out, and then annotate it with @configuration properties. The configuration properties will take a string that matches the configuration block, and then add a configuration inject annotation. And here we can inject the my config. And let's write a function that would leverage this my config object to return the name in the configuration. So return type is a string, return hello, then my config dot name. And let's run the test. We're going to do something similar to what we've been doing. We'll define an expected value and then call the appropriate function and then check the returned value from the function with our expected value. So we'll just copy what we've done before and modify it a bit. Let's specify the correct function. Annotate our test function with @test. Let's run the test. Awesome, the test passed. So these are just a few ways that you can pull configuration values from your configuration file. There are some other ways that you can pull in configuration values, but these are the ones that we're going to cover in this. Feel free to take a look at the documentation to learn more. See you in the next one. Welcome back. In this lesson, we're going to create a product entity class and a product entity DTO. Let's create a new package. We'll call it the entities package. Our new product entities class will be created inside the entities package. Let's also create the DTO package. In the entities package, I'm going to create a product entities class. It's going to be a data class. And let's give it some properties. A product should have a product name, a description, let's add an internal ID. We would use the internal ID to illustrate one simple use case for data transfer objects. Let's add a unit price. Let's add an image URL for the product. Next, we're going to create a data transfer object class. The data transfer object class will have the same attributes except the internal ID. The idea is to hide the internal ID. So whenever we retrieve the product entity from the database, we populate a data transfer object and return that to the caller. That's it. We created a product entity class and a product DTO class. In the next lesson, we will create a repository that will make use of these two classes that we just created. See you there. Welcome back. In the previous lesson, we created a very simple product entity class. In this lesson, we're going to create a product repository class that can interact with the database. I'll create a new class called product repository. To enable dependency injection, we'll need to annotate this class with @singleton. This new repository class will be used at the layer closest to the database. All access to the database will be through this class. Next, let's define some methods for this repository. We need a method for saving things into the database. We need a method for updating data that is already stored in the database. Let's call it the update function. We need a method for retrieving data from the database. We can call our function find by ID, which means that given a particular ID, the function should be able to retrieve the record in the database that has that ID. The function should return an instance of product entity. We need a method for deleting data that is already stored. Depending on your own requirement, you might have to define other methods that would retrieve data based on some specific properties or attribute values of the records that you have stored. And a list method that would allow us to retrieve the list of records in the database. For now, let's just return an empty list. I think we have our repository function set up, but we haven't implemented anything yet. In the next lesson, we're going to write tests for these functions. Welcome back. In this lesson, we're going to create a test class for the repository. I'm going to create a new package called the repositories package. Inside that package, I'm going to create the product repository test class. Annotate the class with @micronaut test. In the test class, we can create functions that will test the expected behavior of the repository functions. As usual, we need to inject the repository class because we want to test the methods. Our first test will be to make sure that the repository can actually save records in the database. We do not want to start thinking about what the final database will be, whether it's relational, Postgres or MySQL, or non-relational, Mongo, Redis, Cassandra, etc. We could implement something that stores data in memory for now. We'll need to create a sample product entity data, and the repository function should be able to take this product entity and store it in some data store. The repository should also have a function that can return the stored data whenever we need it. Let's add some properties to our sample product entity. Let's add a product name and product description. I'm going to assign a random value to the cost. Kotlin has a nice random value function. I'm going to use it to create a random value. I want to use random values between 10 and 1000. I used the wrong random class here. I need to use the correct one. When you want to use random value function, make sure you import the one from Kotlin, if you're using Kotlin. I'll populate the image URL field. Feel free to add any image URL that you like. I'm going to use something simple, something that doesn't exist. The reason I added this internal ID is to illustrate a very basic use case for data transfer objects. The internal ID may be generated during the creation of the entity, and we don't want to expose it. We want to use the data transfer object to hide that internal ID. Let's add a regular ID attribute to this product entity class. So now that we have our product entity, the next thing we want to do is to call the product repository save function. We'll pass the product entity into that save function. Let's add the parameter to the function. And the next thing we want to do is to try to retrieve that record using the repository. So after we retrieve the record, we can now test and validate what was returned. Let's add our assertion. So we want to assert equals product entity and result. Import the appropriate assertion function. Because we have not implemented the functions yet, I believe this will fail. Let's annotate our test function and then let's run the test. Our test failed. Let's find out why. the return value is null, which means that nothing was saved or even nothing was returned. So let's try to implement the save function. But first, we'll have to figure out where to store the data. Let's use an in-memory data store. Let's use a map, a concurrent hash map. The concurrent hash map can handle multiple threads. That's why I'm using it here. So for our save function, we'll take the ID of the incoming record and then map it to the record itself. For the find by ID method or function, we'll take the ID, we'll check the memory to see if that ID is in that memory. If the ID is present, then we return the value associated with that key. If not, we return null. So now that we have this, let's run our test again. Awesome, our test passed. Welcome back. In the previous lesson, we implemented the save function and the find by ID function. In this lesson, we're going to implement the list function. But first, we're going to write a test for it. Let me close all the other open files that we don't need here. Let's create a new function called list function returns correct records. Let's reuse the product entity that we created initially. Let's extract that into a function, a private function. This helper function should be inline. So inside the list test function, we can just call product entity function. and then it will create a new product entity instance for us. Next, let's create a list of product entity items. And then for each item in that list, we call the save function. Let's use a map function so we can retain the list of items. And we can iterate over all items in that list and call the save function. I'll move the function call into the loop. Now let's call the list function. First, we're going to check that the returned values is equal to the list that we have and that the list is not empty. Let's run our test. The test failed, so it's time for us to implement the function and make the test pass. In our product repository list function, we can create a list and then retrieve the values from the map, add all the values from the map into the list, and return the list. Let's run the test again. Our test passed. That's good. In the next lesson, we will look at the update function. Welcome back. In this lesson, we are going to implement the update method. Let's create a new test function. We can call it update function modifies the correct record with correct value. As usual, we'll save a record and then modify the record and call the update function. After the update function is called, I'll retrieve the record and check it against what we tried to update to make sure it was actually updated. I'll start by creating a new product entity instance. Let's save the product entity to the database. I'll make a copy of the saved record so we can modify it. The copy function is a convenient way to clone an object and also make changes to your copy of that object. We're going to change all the properties of this object except the object ID. Here's our modified product entity instance. It has the same ID as the initial record we saved. Then I'll call the repository update function and pass the modified record instance. Next, we will call the findById function with the record ID and then check if the returned record is equal to the one that we passed into the up. This test is supposed to fail, and then we're going to implement the function to make the test pass. Let's run. As expected, the test failed. Let us implement the update function. In the update function implementation, we're going to check if the record exists. If it exists, we replace the old record. If it doesn't exist, we can decide what we want to do. We can either do nothing Well, in this case, let's throw an exception. For our exception, we need a custom exception class. We can call it my record not found exception. The custom exception will be a subclass of exception in this case and say no record with the given ID. Let's add that into a variable. I'll run the test again. We've completed that. Our test passed. Oh, right. Let's add another test case. We want to add an extra test case so that we can verify how the update function behaves when the record does not exist. I'll try to update a record that does not exist and then ensure that it fails. There are several ways to do this. We can wrap this inside a try-catch block, and if the exception is not thrown, we can add a descriptive message to the failure function. And here you can now catch the exception and do something with it. Assert that it's the expected type of exception. And checking that the exception thrown is a record not found exception. We expect a message from the exception, and in our test, we can test for that message. Let's run the test. Our test passed. In the next lesson, we will implement the delete function. Welcome back. In the previous lesson, we implemented the update function with tests. In this lesson, we're going to implement the delete function with tests. I'll write a test to verify that the delete function works as expected. Let's create a new test function. I'll call it delete by ID removes the correct record from the database. As usual, I have to annotate each test function with the test annotation. I will create a product entity. Save the product. Call the delete function and then make sure that the record was actually deleted. If I call the find by ID function with the deleted record ID as parameter, the function should return null. Let's create some records and save those records. We will store the instances in a list. And then for each item in the list, we call the product repository save function and pass the item as parameter. When the delete function is called, it should delete only the record that was specified, not everything in the database. I will call the delete function and pass it the ID of the first record. If find by ID is called with the ID of the deleted record, it should return null. I'll accept that the response is null. It would be good to check that the second record was not deleted. Let's run the test. As expected, the test failed. Let's try to make the test to pass. It's time to implement a working function. We'll check the memory to see if the item exists. If it's present in memory, we will remove it from the memory. If the record is not present in memory, we can throw an exception. You can decide to do nothing if you want. When you add such an exception, it's good practice to add a test case to make sure that scenario is also covered. I'll leave that for you to do as an exercise. Let's run our test. Our test passed. In the next lesson, we will start looking at controllers. See you there. Welcome back. In the previous lesson, we wrote a test for the delete function and implemented the function to make the test pass. In this section, we will learn how to implement a getEndpoint. We need to create a new controller class for that. And we'll call that controller the product controller. As usual, for any new controller in Micronaut, you have to annotate it with a controller, as I have done here. I'll create a controller test. Annotate the test class with that Micronaut test. Inject a product repository instance because we'll need it to save data. For our getEndpoint test, I want to check that the endpoint returns correct data. Let's add a path to our controller annotation /products. I'll create some empty functions that we will implement later. Each endpoint function in the controller needs to be annotated with an appropriate HTTP method annotation. We'll annotate our get function with the get annotation. This annotation means that every time the application receives a get request with URL/product, then this function will handle the request. If you receive a get request with a /ID, then the function is going to handle the request. Let's inject our product repository into the controller. Let's rename the test function to something more appropriate. Say get returns correct record. I'm going to create a new HTTP request with the required URL. When you import the HTTP request class, make sure you import it from the Micronaut package. I want to import the product entity. Recall that we have a helper function inside one of our tests. So now that we need that same function in our controller, it is probably a good idea to move that function out into some kind of utility class. For our GET request, we'll need to import that product entity function. Next thing we'll do is use the repository to save the record. And then we could call the endpoint to return that record. Let's add an extension function to the product entity class. That extension function is what we can use to convert the entity to a product DTO class. In this case, what we're implementing is a simple function. The function maps the attributes of the current product entity to properties of a product DTO instance. Now, let's write another function that would convert from product DTO to entity. These are convenience methods that would help us as we implement our other endpoint functions. We have two DTO and two entity function extension functions back to our HTTP GET request. To make a request, we'll need to create a client. I realized that we didn't have a client here. Let's create a HTTP client. A Micronaut client will allow us to send HTTP requests. We are not going to cover the client for this course. Please refer to the documentation to take a deep dive as needed. Inject it. Also, remember to inject from the Micronaut package. There are two methods you can use: .retrieve or .exchange. .exchange will return the entire HTTP response. .retrieve most of the time will just return the body of the response. If you are interested in the response code, then use .exchange. In this case, we want to use .retrieve. So here I'll send a GET request. This would most certainly fail. We need to assert that the response is not null. We also need to check that the response matches what we expect. Let's run the test. No host has been specified and we have to add a host. I've added an ID to the URL and it matches the host to the controller annotation. Let's run the test again. Now we're getting a different error. We're making progress. Inside the function, we simply take the ID gotten from the request and then call the appropriate repository function with that ID. And if the record is available, all we need to do is to return the record. In this case, we can set the HTTP response to OK and then return the record. Here we return the raw product entity, but we could have also converted it to a product DTO. You can do that on your own. Let's run the test again. Our test passed. In the next lesson, we'll implement the controller save function. Welcome back. In the previous lesson, we implemented a getting point for our controller. In this lesson, we're going to implement the save function for our controller. As usual, we're going to write a test and implement the save function to make the test pass. When coming up with a name for your test function, you can come up with something that is descriptive enough. I run out of ideas too, but anything that describes what the test ought to do is fine. Here we use the name save saves or persists correct record. We will use a DTO in our post request body. We will get one by calling our extension function on a product entity instance. The URL will be to the same product endpoint, and we will pass the DTO to the function. Let's modify the rest of the function to suit our needs. We'll add our assertion to verify the response status. I'll check the response from the post and also that the GET request will return the record that we just saved. For this particular request, we're interested in the HTTP status of the request, so we're going to make a request and then check for the status of the response. After the post request is made, we want to make a GET request to retrieve the record. Let's copy some code from our previous test and modify it for this purpose. I'll rename some variables. Then we should write assertions against that returned record. Let's run the test. The test failed as expected. In the next lesson, we will implement the actual function that will save records and make the test pass. Welcome back. In the previous lesson, we wrote a test for the controller post endpoint. In this lesson, we will implement the endpoint and make the test to pass. Our save endpoint function will be annotated with a post to show that it should handle a post request to this endpoint. And we annotate the function parameter with a body. The received JSON will be bound to an instance of product.dtl. Next, we want to call our repository instance to save the record. We will need to call the extension function that we created in our previous lesson. I cannot access our extension functions because we created them inside the test utility class. Let's create a new class called DataUtil. Let's code the extension functions and paste them inside the DataUtil class. Let's import the functions where they are used and clean up old references. Our response could be HTTP created response with a short message. Since we are returning a string with the response, let's treat the HTTP request and change the type to a string. Let's run the test. Our test failed. Something is different about the return, and that is the number. Because it has to do with big decimal, we can just tweak our test and check if the value falls within a certain range. We can use the big decimal equals method to check for equality. Let's use the compare to function to make sure that those two values are equal. And that's it. Let's run the test again. The test passed. That's it for the test. In our next lesson, we'll start work on the putting point. Welcome back. In the previous lesson, we touched on the save function. In this lesson, we'll focus on the update function. For the update function, we'll use a put request. We can copy one of our tests, paste it, and modify it since we already have some of the things that we need inside the test. As usual, following the same pattern, we'll create data and then try to make a request to update the record. We can verify that the request we made was handled in the way that we expect. Change the request to HTTP put and then set what kind of argument that we're sending in with the request. We're going to create a sample record, and that's the record that we would pass into the HTTP put request. I'll just use a big decimal of 1 for the test. It would be good to check the response when we make that request and make sure that the response code from that request matches what we expect. After we make the update, the next step would be to make an actual GET request to retrieve that record. When the record is retrieved, we can check that the record retrieved matches the modified record that we sent in the post request earlier. Let's refactor the assertions a bit. Let's run the test and see. As expected, it failed because the method has not been implemented. We'll implement that method in the next lesson. Welcome. In this lesson, we are going to implement the put method. In the previous lesson, we implemented a test for the put function. This time, we are going to implement the function itself and make that test pass. As usual, we have annotated the method with put and annotated the product TO with a body annotation. We will simply call the product repository.update method. Here you can decide on what you want to return. In this case, I just want to return an HTTP response OK with the message updated. Let's run the test. Awesome, it passed. In the next lesson, we will implement the delete test. Welcome back. In this lesson, we are going to implement the delete function. This will be a HTTP delete method and we should annotate the function with a delete. Let's reuse the test that we wrote before and modify it. It deletes or removes the current record from the database. Okay. We should pass in the ID of the record that we want to delete here. Let's modify this to the appropriate. We want to check that the status is no content. In this case, we expect once we execute the delete function, it should return a no content status. We just make a request and see if there is a response. If the response comes back, we need to check to make sure it's what we expect. After the request, let's make sure that the record doesn't exist. Let's run the test. As usual, because this function has not been implemented, our test should fail. As we can see, our test failed with method not allowed. We're going to implement the function in the next lesson. We'll come back. In the previous lesson, we wrote a test for the delete endpoint. In this lesson, we will implement the controller endpoint to handle HTTP delete requests. As usual, we annotate the function with a delete. Once we get an HTTP request of type delete, this function should handle that request. The function takes a parameter of ID, and we simply just call the repository instance. I'll call the deleted_id method. In some cases, you might decide to use another layer that calls the repository, something like a service layer. In this case, this is really simple, so that's why we're calling the repository directly. Here we're returning no content, which is what we expect from the test. Let's run the test. As you can see, the test did not pass. Let's find out why it didn't pass. The response body is empty. After we deleted the record and made a request to retrieve the item, an exception should be thrown. Let's make sure that the exception is thrown. Let's run the test. Alright, that's it, our test passed. Next is the list function, and you can implement this yourself. We'll come back. In this lesson, we're going to write a test for the list function. Let's copy one of our existing functions and modify it. Make sure that it returns the list of records from the database. And I'll send a GET request. I'll save the data and then check that the method returns a list of items. Check the size of the items returned. Run the test. Okay, our test failed. In the next lesson, we are going to implement the function and make the test pass. Welcome back. In this lesson, we are going to implement the list function. I'm simply going to call the repository list function and then return the list. In this case, I want to convert the records to DTO objects and then return that. Let's run the test. The test passed. In our next lesson, we are going to add a relational database and configure Flyware. Welcome back. In this lesson, we're going to go over the process for adding a database. I already prepared a Docker Compose file for this. You will need to install Docker if you have not already done so. In the Docker file, I have added MySQL and Adminer. Adminer is a database client that we'll use to look at the database from time to time. I'm going to add Flyware. Flyware allows us to run migrations and manage changes to the database. I'll add MySQL driver. In this case, I'm using MySQL connector J version 8032, Micronaut JDBC, and Hikari. Next, I'll add Micronaut data JDBC. It's recommended to add the annotation processor near the top of your dependencies block. Next, I'll add Flyware inside the plugins block, so we'll have access to some useful Flyware commands and tasks. Let's refresh the build to make sure everything is there. I think we're almost good to go. Let's see if our tasks are here. As you can see, the Flyware tasks are now available for us to use. Let's run Gradle clean. Next, I'll have to add the data sources. This is the bit of config that application will use to connect to the database. The data sources block can have a default data source block. The default block will need a URL, a username, and password. We will use root for the username for now. Don't use root if you're working in production. It's not recommended for security reasons. And we'll use password as password. I'm using credentials that match what I have in the Docker Compose file that I showed earlier. The data sources block is similar to the flyway block. One subtle difference is that instead of username, we use user in the flyway block. Clean schema tells flyway to delete and recreate the tables each time you run the app. It could be good during development. It looks like we're on the right track. For flyway to start doing its job, we'll need to add migration scripts inside the source main resources folder. Here we create a table in our database with the properties of the records we want to save. The record must have an ID, product name, the description, image URL, and unit price. Okay, let's run it and see if it works. It migrated the schema and the application is running. Let's check if the table exists. I'll add another property to this table and then we run. Because we have clean schema set to true, flyway will delete the table and recreate it. Okay, the internal ID has been added. In the next lesson, we will start implementing repository functions that will help us interact with the database. Welcome back. In this lesson, we'll be looking at implementing the save function using JDBC. For us to do that, we need to annotate the product entity. I've annotated the product entity class with a mapped entity. That means we are mapping the product entity class to the product table. Then our naming strategy is underscore separated lowercase. It means that in the database, the names are lowercase and separated by underscores. We will need to annotate the property that represents the primary key with an ID to show that it's the primary key. Then, we need to create a repository that will enable us to interact with the database. It will be an interface that extends CRUD repository. For JDBC, you will need to annotate it with a JDBC repository. It's recommended to choose a dialect. In this case, we're using MySQL dialect. If you're using Postgres, you would select Postgres as your dialect. The product entity tells the library what the main class maps to the database table. The string property specifies the data type of the primary key. Let's make this an interface. One thing that is cool about this JDBC repository is that it has a lot of those methods already implemented for us. The basic create, read, update, and delete. Let's test that out now. I'll copy the existing test and modify it. Now we've just modified the can-save product entity test function. And we'll run that. The test passed. We didn't even need to write much code. Notice that all we had to do was to create an interface that extends the CRUD repository. Let's take a closer look at the CRUD repository interface. If you want to implement a custom method, you are free to do that as well. Let's define one inside the interface and then write a query for that function. In this case, I'm going to run the list function and see if it will pass the test. Awesome, it passed the test. Welcome back. In our previous lesson, we introduced Micronaut JDBC and implemented a repository. In this lesson, we're going to look at implementing a get endpoint that uses the Micronaut JDBC repository. Let's start by adding the repository that we created in our previous lesson. and we'll create a function similar to the already existing get endpoint. We'll copy the existing function and modify it. Modify the route. Use /JDBC so we can distinguish the endpoint. Then change the function name to get with JDBC. Let's reference the correct repository instance and call the findById function. The get function is supposed to return a record, but it returns an optional. The optional is used to represent a value that may or may not be present. That's one difference between JDBC repository and the in-memory repository we created in one of our previous lessons. Let me add an if statement to check if the record was returned. If something is present, we will return the value. Else, we return a bad request response. Let's write a test to make sure it works. I'm going to copy the already existing test and make some modifications to it. I'm going to save the record via a post request. Then make a get request to retrieve the record since we're doing this through the controller. We have not yet implemented a post endpoint that uses JDBC, and we'll do that shortly. Let's run our test. Okay, the test failed. It's a bad request on /products. Let's add a controller post endpoint that uses JDBC to save records. I'll reuse what we did before. Copy and paste. We'll add the correct route and reference the correct repository instance. Let's modify the post request in the test and add the correct URL. I'll run the test again. Our test passed. Awesome. In the next lesson, we will integrate Juke and use it to perform CRUD operations. Welcome back. In this lesson, we will integrate Juke into our project and use it. Juke is a database mapping library for interacting with database management systems. It is compatible with MySQL, Postgres, and some others. To integrate Juke, you need to add the necessary dependencies inside your project build.gradle file. First thing we need to do is to add Micronaut Juke. Let's see if that will be built. Then let's add a plugin for Juke. Now I can run the build again and make sure that it builds successfully. Then we add a Juke generator entry inside the dependencies block. It was made available by the plugin that we just added. We have to add the MySQL driver. Let's run the build again and make sure that it is successful. Now it's time to configure Juke. Flyway and Juke would need the information about how to connect to the database. We need the database credentials. For now, I choose to keep them here in this file, but I would normally reference them from another place. For the purpose of this course, we'll just keep it here for simplicity. This is our database URL, username, and password with the schema as well. We have all of that defined here. And we're going to make use of the pieces of information here in the next block. In the Flyway block, we'll add the username, the URL, and the password. This allows Flyway to have access to the database. As you will see shortly, we need to define a dependency between the Juke and Flyway tasks because Juke needs Flyway to run first before it generates files based on the tables in the database. Let's configure Juke here. Inside this Juke block, we will create a configurations block. Inside the configurations block, we'll add our Juke configuration. We'll define the database driver and credentials. Our driver is mysql.cj.jdbc.driver. Let's configure JDBC and add the driver, URL, username, password. Next, we have to configure the generator. So we have database.apply. Please refer to the online documentation for Juke to learn more and take a deep dive. Inside this generator database block, we'll define the input schema and then properties for the generator. Here, I'm telling Juke how I want it to generate some of my files. We've added some config to the Juke block, but we also need to add some others. Now I want to tell Juke where to save the files that it generates, including the package name for the classes. Next, I'll have to modify the cleanup task a little bit so that each time we run a Gradle clean task, the generated files will also be deleted. That way we can always start with a clean build. Let's tie this up with flyway migrate task. Let's make flyway migrate tasks to run before every generate Juke task. We also want the generate Juke task to run before the compile task. If not, application compilation might fail. Now let's run the app and see. It looks like it got built successfully. But we need to actually run the application and see if it's starting up. We're trying to start it up. We see that there's an error here, unable to create the repository. It means we don't have something, because it's unable to create the repository. Something is missing. Okay, so no database found to handle the request. Let's clean it. Let's add a build script here. Looks like this is what we missed. Add flyway to our class path. Let's try to run our application again. From the logs, we can see flyware and Juke-related activity. There are no errors reported. Our application just started. Awesome. Juke also created a generated folder with a bunch of files. In the next lesson, we will create a DSL context for Juke to enable us to execute queries. Welcome back. In this lesson, we are going to create a factory class that will be used to configure a DSL context for use within our application. We would need to create a package for factory classes. That is where we'll keep our factory classes. A factory is a mechanism of creating and configuring objects at runtime. In this case, we want a class that can create DSL contexts for us. To create a factory class, annotate it with a factory. Let's create a function that will be used to configure the DSL context. The singleton annotation is required. Inject the configuration so Micronaut would make an instance available for us to use. On the second thought, let's use a data source to get connection properties. The data source has information necessary for connecting to the database. We'll return DSL dot using data source, comma, SQL dialect.mysql. Let's add a test to make sure that when the application starts, we can actually access the DSL context. I'll use an instance of the application context to do it. We want a bin of type DSL context. Run the test. The test passed. I'll move that test out into a separate class. Let's run the test again. The test passed. In our next lesson, we'll make a Juke repository and use that to test some of the basic functions like list, save, update, delete, and delete all. Welcome back. In this lesson, we're going to learn how to create a Juke repository and use that to implement some of the basic functions that we've looked at so far, like the find by ID, save, update, delete. Juke is a little bit different. Let's create a repository and see how. Let's remove some of the functions that we don't need for now. Juke works with records and not entities. Normally, I like dependencies pointing upward from lower levels. That is, use the DTO inside the repository, so other classes at a higher level of abstraction won't need to know about Juke record classes. However, for this lesson, I am going to use records inside the repository. Let's change all the product entities to records. Let's do a little bit of cleanup here and then inject the DSL context. For our save function, we'll use a DSL context. Notice how the syntax is similar to writing SQL queries. Let's create a test class for this, and we can modify the functions in the test class to match our Juke implementation. Let's change our product entity to DTO. For this purpose, we can map the product entity directly into a product record. Let's create an extension function here that we can reuse in other places. We can now map directly from product entity into product record. Let's modify our test a bit. We have a find by ID function. Let's implement that. Similar to SQL, this is almost like a select function. Select from table where product.id equal to the ID, fetch into product record. In the test, we can check if the record is not null. Then we can check the properties of the record returned. Let's comment out the pieces of code that we don't need. Let's run the test. It passed. In our next lesson, we will learn how to implement a list function with Duke. Welcome back. In this lesson, we are going to implement the list function. Let's start by writing a test for it. We're going to create a product record list and save the records. Then we're going to call the repository to list those records files, and of course check that the records are equal. Let's implement the list function. Select from products. Fetch into product. Record class.java. Return that. Let's run the test. One thing that we haven't done here is to determine the order of the records. When we run the test, we see that the records are coming back, but they may not be in the same order as the list we want to compare with. Let's make sure. Let's clean up some things first before we take a look at that. Let's make sure that for each time we run the test, we delete the records. Actually, we don't have to delete all the records. We just need to check that they returned in the same order. How are we going to handle that? Let's check the size of the returned records with the number we tried to save. We could order the records by ID and then check each one to make sure it matches what we expect. Let's run the test. The test passed. In the next lesson, we'll start implementing the update function. Welcome back. In this lesson, we're going to implement the update function for Juke. We'll start with the test. We will use a test we wrote in a previous lesson and modify it. We need to convert this entity to a record. Let's check our find by ID. Find by ID does not return an optional, so we'll remove the is present and also remove the get method. We have to ensure that they are set equals is of the same data type. Let's run the test. The test is expected to fail because we have not yet implemented the update function, and that's what we're going to do next. To implement it, we use DSL context update table, set the record, and execute. If you want a certain kind of update behavior, you can implement that with Juke as well. An example is if you want to create a new record, if the record does not exist, or update the record if it already exists. Those are things that you can explore depending on your use case. Let's run our test again, wait for it to execute. As you can see, our test passed. See you in the next lesson. Welcome back. In this lesson, we are going to implement the delete function using Juke. We have a previously written test that we can use. What we need to do is to modify it slightly. We need to change all the entities to records and remove the optional methods. Because our current implementation for delete by ID does not throw an exception, we don't need to check if an exception was thrown. Let's run the test. The test is running. Our test failed. Let's find out why it failed. We see that our delete method has not been implemented yet, and that's what we're going to implement now. As usual, we'll call on the DSL context and delete from table or product where the product ID equals the given ID, and then we execute. Let's run the test again. The test is running. Our test passed. See you in the next one. Welcome back. In this lesson, we're going to implement a simple delete all function for Juke. If you recall, we implemented a delete all function in one of our previous lessons, but we did not write a test for it. Let's uncomment the delete all function test and modify it. Let's implement a count function that will return the number of records in our database table. The idea is to call the delete all function and then call the count function to return the number of records in the database. We can see that the test failed. Let's find out why it failed. Okay, it failed because we didn't add an execute function call after the query. I'll run the test again. This time it passed. Great. It's good practice to write tests for your functions. If you want, you can do some refactoring. Welcome back. In this lesson, we will implement a controller route that makes use of Juke to persist data. Similar to what we did in a previous lesson with JDBC repository that we created. Remember that we wrote tests already for the repository. All we have to do is copy the test that we wrote for JDBC, then modify it a bit and adapt it to Juke. Let's run the test. I expect it to fail. We'll inject a Duke repository into the controller. Let's copy some functions and modify them accordingly. First, we modify the URI. We want the getEndpoint to return a product DTO. Make sure we are calling the Duke repository. I'll modify the rest of the function. For the post endpoint, let's modify the URI and the function name. We need to call the Duke repository save method. For Duke, we need to annotate the save function with a transactional, and so we have to open the class and functions. Let's run the test. The test passed. That's great. In the next section, we'll move on to Redis. In our previous lessons, we learned how to integrate JDBC, and we also learned how to integrate and use Duke. We did some test-driven development along the way. In our next lesson, we will integrate Redis and implement caching for one of our endpoints. Welcome back. In this lesson, we're going to integrate Redis. Redis is a high-speed, in-memory data store that is commonly used as a caching solution, but it has so many other use cases beyond just caching. In this lesson, we're going to use it for temporary storage and caching. First thing we'll need to do is to add the required dependencies. Here, we're going to add the dependencies for Redis, which is io.micronaut.redis, micronaut redis lattice. There are several drivers you can use with Redis, but for this lesson, we're going to use the latest driver. After adding Redis, we need to add some configuration for it. Here, like all data stores, you need a host, a password. And then inside your Docker Compose, let's add Redis so that we will be able to access it locally via Docker. Our image is Redis. Restart always. Let's expose the required port, which is port 6379. We're mapping our container port to our machine port. Let's set a log level for our Redis server and set a password. Now let's run the Docker Composer. Redis instance is now up and running. That's it. In the next lesson, we'll start playing around with Redis. Welcome back. In our previous lesson, we integrated Redis. In this lesson, we're going to implement a cache get endpoint. We're going to use Redis as a cache. The cache is useful when you have a high traffic application and you hit the database frequently for data. For those cases, you may not want to hit the database as often to get the data. You could store the result of a query in the cache so that you don't hit the database each time you get a request. To get started, we are going to need a stateful Redis connection, and we can get that from a Redis client. A Redis client is available because we already added the dependency. I'm going to check if the record requested by the client is in the cache. If it is in the cache, we return the record. If it is not in the cache, we query the database, retrieve the record, and then store it in the cache before returning it to a user. Here, for the record that we retrieve from the cache, we have to deserialize it into an object and then return the object. For the case where the item is not in the cache, we want to also save that item in the cache. If we get the item using the repository, then we should store it in the cache in case another request comes in. From all the options, one can even set expiry date for the data that is in the cache. It's also possible to store data in the cache without an expiry date. We want to save our data as string. You're free to use other formats acceptable for your use case, but in this case, I want to just use a string type. We'll set the retention time to 10 seconds, so after 10 seconds, it will be kicked out of the cache. The next thing we're going to do is to figure out a way to test this. Let's make sure that the endpoint still works, that the test still passes. And we can see that the test passed. One way we can test this is to make a call to the endpoint and then check that the information is stored in the cache. We're going to save to a repository, make a call to retrieve the information from the endpoint, and then right after that call, we can check to see if the data was stored in the cache using the ID. That's what I'm trying to do here. And I realized that for the cache value, if you recall, we stored that as JSON. So we need to convert either the return value to an object or the object that we expect to JSON. In this case, we'll just convert the return value and then compare that with what we originally retrieved to make sure that the data was stored in the cache. Let's run the test. Okay, so the test passed. You can take that further by making a second request and then checking that it still passed. In that second request, we expect that the return value should be from the cache. So I will leave that to you as an exercise. We'll come back. In the previous lesson, we touched on Redis. I encourage you to play around and explore other use cases for Redis. In this lesson, we are going to integrate Kafka and implement a simple use case in the following lesson. I encourage you to play around with Kafka after we are done. Kafka requires Zookeeper as of the time that this lesson was prepared, and we're going to add Zookeeper to our Docker Compose file. Let's name the container learner Zookeeper and the host name Zookeeper, so we can reference it from Kafka. Let's set the port to 2181. If you are already familiar with creating this, feel free to skip forward. Service name Zookeeper. Zookeeper client port to 2181. These are some of the environment variables we want to set. Running this locally would allow us to write some tests. It's possible that you can also do all of these things with test containers. I wanted to use Docker for this lesson, but you're also free to explore test containers. They are portable containers that you can use for your testing, and you can have access to Kafka and other containers available via test containers. Here is Kafka. We're going to use the Confluent Kafka image, and the ports will be port 1992. Let's say that it depends on Zookeeper. Which means that before this runs, Zookeeper has to be up and running. And for the environment, we'll just set a couple of environment variables, including the broker. We'll set the listener security protocol map, and plain text. and the Kafka interbroker listener name, plaintext. Kafka advertised listeners, plaintext, localhost 1992. Kafka auto create topic. We want to enable it so that testing will be easier. If a producer tries to publish to a topic, Kafka would auto create a topic if it didn't exist. I'll set the replication factor to 1 and just leave it there. There are other options you can set. I encourage you to explore, but these are the options that we need. The ones that we have so far are sufficient for our lessons. Let's use Offset Explorer to check and ensure that we can see Kafka and we can see Zookeeper. We can see brokers topics. In this case, we don't have anything there. We might return to it when we start posting messages into the topics. I'll set some configs, set some for consumers topics. I can use my first topic. And that's it for now. In the next lesson, we'll try to post some messages into topics and write some tests. We'll implement the Kafka client in the next lesson. In this lesson, we're going to create a Kafka client. A client is a piece of code that we can use to post messages or events into a topic. Create a package. The new class, Kafka Client class. And annotate it with Kafka Client. This is an interface that would be implemented for us. Let's add Micronaut Kafka to the build.gradle file. Make sure it's available. Import the client. And we can implement the send function where we define a key. A key allows Kafka to arrange the messages and decide what partition gets the message. And that's it. We've just created a client as simple as that. In the next lesson, we'll try to use that client to post a message. Welcome back. In this lesson, we're going to implement a Kafka listener. We already have a client. First, we need to create a scheduled job to help us verify that our client can actually post messages into a topic. To do that, let's create a configuration. The configuration class will allow us to pull the properties that we've set in the application.yml. For each configuration, you need to annotate with the configuration properties and name, put the value as the name or the path in the application.yml. Kafka.consumers matches my path in the application.yml. And then the property should match the name of the config. In this case, it is topics. Now that we have the config, let's go ahead and create a scheduled message publisher, or we can call it anything we want, basically a sender. Let's make this class a singleton and make sure it doesn't run in a test environment. We can specify that by using the requires annotation and specifying the condition, which is not environment test. And let's inject the Kafka client and then write the function, the scheduled function that will be executed every say 10 seconds or 5 seconds. In this case, it's good to add a key to the send function. We'll have the message that we want to send. Hello, Kafka. And we're going to include a timestamp to distinguish between messages and then call on Kafka client.send function. We need our consumer config so we can retrieve an appropriate topic to post our messages to. We can use the first one. Use a random string as our key. The scheduled annotation allows the ability to set a schedule for the function to run. For example, the function can run every 10 seconds. I'll add a logger. This logger will give us some visibility into what's happening with the class. Whenever the function executes, we'll see something in the console. Publishing message to topic. So that's fine. Let's create our listener. For Kafka listeners, you need to annotate with Kafka listener. And then you can add the group ID and other properties. I encourage you to explore the documentation and see all the available options. Each listener has to have a receive method that will be called, and I can specify some parameters that the framework can use to pass appropriate data into the function. Take a look at the documentation to see all the available options. Here I'm going to log the message. Let's see if our scheduled job runs at the given intervals. I'm starting the application. Let's wait for our application to start up and look at the logs and see if we can see that publishing. Okay, it's publishing. You can see publishing to Kafka. We can shut down the application and continue our implementation. On the receive function, I need to specify a topic. Here is another way to reference the configuration. In this case, this receive function is going to listen to all the topics specified in the application.yml. If I run the application again, we should see login for publishing and login for receiving. Awesome. Implementation is working. In the next lesson, we will write integration tests so we don't spend a lot of time on manual verification. Welcome back. In this lesson, we will learn how to use integration tests to verify that our Kafka setup works and we can publish messages. I'll create a new class and annotate it with a Micronaut test. We'll need to inject required objects, but we'll create a consumer for the test first. The consumer is going to retrieve messages and we can verify that what we published was received. That's the approach we're going to take for this integration test. The requires annotation ensures that this is only available for test environments. Let's create a receive function that takes a key and message parameter. Let's specify a topic. The topic can be my test topic. Okay, let's add a container that we can use to store all the received messages. For each message received, we simply store it in the received messages list. Then we can compare a list of published messages with the list of received messages to make sure that the consumer received every message that was published. That's it for the test consumer. Now let's write an actual test. Let's inject the consumer first and then inject the Kafka client. I'll create 5 messages. You can choose any number you like. We'll need to create the message and call the client.send function. The topic is the one that we specified. We want to use that and then specify a key and a message. Let's add a logger here for visibility. Now we should be able to check that the number of messages published by the client is the same as the messages received by the consumer. It will take some time for all those messages to get published and some time for all of them to be received. Let's use a waitility to add some wait time for the assertions. Then let's add a setup function that ensures that our containers are cleared before each test. In addition, let's add a few seconds sleep to the test. Let's run the test. It appears to be publishing and receiving. Our test failed. Let's find out why. I did not add the received messages to a list. I'll run the test again. It passed. In our next lesson, we'll go through the typical workflow where a listener has to retrieve messages from a topic and persist the messages to the database. In this lesson, we're going to set up a publisher to produce messages, then a listener will retrieve the message and use our Juke repository to save the contents of that message into a database. This is like a typical flow in many apps that have integrated Kafka. We are going to implement that example, and then you can explore other use cases yourself. I'm going to modify our scheduled message sender and make it send the product DTO as JSON. That way, on the listener side, we can retrieve that JSON, do something with it, and then save it. Let's create a product DTO and give the product a name. You can use any name you like. I'll use PlayStation. This random message generator will send a message every 10 seconds as specified here. Be careful to import the right Kotlin function. Next, we need to convert the product DTO instance to JSON and then publish the JSON. You're free to publish objects if you want. For just this lesson, I'll publish JSON. Now let's go to the Kafka listener. Inside this listener, we are going to use the repository implementation to save the contents of the JSON into the database. Our listener is not yet doing anything, but we'll get it to do something. In here, we convert that JSON back to a product DTO instance, and then we use the repository to save the product DTO. That's it. At the next lesson, we can write a test for it. Welcome back. In this lesson, we are going to implement a test for the Duke Kafka function we wrote in the previous lesson. We'll create a test class, myKafkaListenerTest, and annotate it with Micronaut test. Inject my Kafka client. We need a client that would publish messages. Let's undo our changes to the scheduled message producer. The listener that we already have will receive and persist the messages. We can verify that the messages have been saved using a repository to check the database. Similar to what we did in the scheduler, but we are going to do it in a test. We will use a waitility to give it a timeout of a few seconds. This is to give some time between publishing and receiving. Let's also assert that a record was found and annotate our test function with the test annotation. Let's get our Docker stack running and then run the test. Our test failed because Kafka wasn't completely initialized. I'll add a brief sleep to allow it to start. That only partially solved the problem. I missed the description on our product, so we have a validation error. Let's add description and run the test again. Good. Our test passed. In the previous section, we learned how to integrate Kafka and we saw Kafka in action. In this section, we're going to set up Mongo and integrate it with Micronaut. We will do it with a new project. Another way you can set up a new project is just open up your console and type them and create and hit enter. You will see an interactive console that you can use to create your project. For this project, we're going to use the Mongo reactive library with Project Reactor. Enter a name for the project. I'm going to call it Product Catalog Number. It'll be similar to what we did in previous lessons, but with a MongoDB data store. Now that our new project has been created, let's look at the build.gradle file. It is a simple build.gradle with two dependencies that we need, the Mongo reactive and the Micronaut reactor library. I created a Docker Compose file for this, so let's take a look at it. In this file, we have the Mongo itself, the username and password. Then we have Mongo Express. Mongo Express is like a client that we can use to look at MongoDB. Let's check the application.yaml and create some basic configurations. The URI should match what we have in the Docker Compose file. And that's it. In the next lesson, we'll set the connection config and start using it. In this lesson, we're going to write simple functions that will interact with MongoDB. You will learn how to perform some important functions like saving data and retrieving data from MongoDB. We have Express and Mongo already set up so we can verify that it's running. Let's create a product entity data class. This is to give you an idea of how it works and how you can go about doing the same when you build your other applications. Let's create a repository class and annotate it with a singleton. Let's inject a Mongo client that we can use to connect to the database. Our first functionality is the save function. I'll create a test file and then a test function. The file would have the same name as the product repository with test added at the end of the file name. Annotate the test file with a Micronaut test. We will use the object mapper to convert product instances to JSON. Let's write a test for the save method. I'll create a product entity instance, give it some attribute values, and then convert it to JSON. Mongo accepts BSON, so we'll use a document class to pass our JSON string into BSON. Next thing we need to do after saving the document is to retrieve the document from Mongo and compare the record returned with the original. There are two functions in the repository class that we need to implement. First is a save and the second is a find. We need to assert that something was returned when we make that call. Let's run the test. The test will fail. It's just an exercise. Then we need to implement the functions to make the test pass. For the save function, we need to call Mongo client.getDatabase. We know that the name of our database is product catalog, and we can pull the product catalog into a variable if we want. Since we know that most of the functions within this repository class will be using the collection, we'll just move it out. I moved it out of the save function because the find function is going to use that collection. Here we return a mono from the function. And for the find document, we're going to implement a find function. If a document is provided, we can call collection.find. If not, we can call a regular collection.find. Let's check that this actually runs. Okay, we'll take a look with Express. We can see that the document is saved. Let's change what we've done here and then just return an actual document. We will implement a separate function for the find. This should be the one that does not take any parameter. If we do a second find, then we can now use the return value for validation. A document will be returned since we're getting that from a reactive type. We'll add some checks inside this block. If it throws an error, we can say that the test failed. Let's run the test. As you can see, the test passed. That's good so far. There are a bunch of other methods you can call on reactive types. If we check our collection using the Mongo Express, we can see that it is saved. Those new data items are saved. And if we decide to add another property, the good thing about Mongo is that it's easy to add properties. It's flexible. If we decide to add another property, we wouldn't really have any schema issues. Your code determines and enforces the schema. Let's add a property and save it. Great, it got saved. Let's check the database. See, the new property was added. So that's a brief overview of Mongo. You can try out other functions like delete, update. You can implement the others as an exercise. And that's it.